All right, welcome back. As you can see, my voice is a little bit not so good because I actually got cold last night. So I'm going to skip this intro and let's jump into the second part already. Again, what are we trying to do? We're trying to look at some integrals and try to use the King's property in calculus, helping us solving integrals without directly figuring out the antiderivative of it. So here you go. Second problem. So with the setup that we are starting off with, this time we're going to look at the function f of x that is equal to e to the quantity cx to the 2k plus 1 power, where c is any real numbers and k is any non-negative integers, meaning that it includes 0. Also, we have our interval from a to b, where this time we'll of course suppose that a is less than b, and in fact we want to have a plus b is equal to 0. In other words, a is equal to negative b or b is equal to negative a, where in this case of course we want b is the bigger one, so we might as well just suppose that b is greater than or equal to 0. And of course a and b are real numbers. We do not include positive and negative infinity, just to make sure that the calculation is going easy. So how are we going to do this? Here we go. So first, let's take a look at the integral itself. Let's give it a name, I. So we have the integral I is from a to b of the derivative dx over 1 plus the function, where the function is given up here, e raised to the c x to the 2k plus 1 power. Good. So let's see what we can do first. First of all, we know that b is equal to negative a. In other words, a is just negative b. So we can now, of course, replace the a by negative b. Good. So next, since we want to use the King's property helping us solving such integral, of course we're going to do that. So by King's property, we are going to get the following. The integral will still be the same based on the property itself, and also the interval that we're taking the integral of will still remain the same, meaning that it will still be from negative b to positive b. And then the only thing that has changed is whenever we see the function f of x, instead of putting x as our inputs, we're going to change it into a plus b minus x. So in this case, we have a plus b, but again, we say that a is just negative b, so we have negative p plus b minus x. And as you guys can see, we have negative b plus b, those two will cancel out. So in fact, what do we have? We now just have the integral from negative b to b of the expression dx over 1 plus f of negative x. So of course, now we need to rewrite what the function f is. The function f is given right here at the beginning, which is e to the c x to k plus 1 power. So how is it going to help us? Well, let me write down in green, and then we will see what we can do. So we have e to the c. Now again, we now have the inputs negative x instead of positive x, so we're going to replace the x by the quantity negative x, and after that we just copy everything else, raise it to 2k plus 1 power. So once we have that, let's notice that here we have x to 2k plus 1 power, meaning that the exponent of x is always odd number, okay? It's always an odd number, meaning if we put a negative inside, it will always giving us a negative result, such that we get negative b to b of d of x, dx over 1 plus e. So again, we're going to put a negative to give us this expression up here. Negative ce, not e, excuse me. Negative cx to 2k plus 1 power. Good. So what should we do next? Well, if we look at our initial expression, we have positive exponent here. Now here we have a negative, but other than that, everything else looks the same. So how can we change this to change this part to here? Well, if we are going to multiply by this expression here, we see that the second term will turn into 1. In other words, if we're multiplying both numerator and denominator by e to the positive cx 2k plus 1 power, like this, we see that in the denominator, the second part is going to cancel with the term that we just put. Then the first part will turn into whatever we have in the in pink. So in fact, we now get e to the cx 2k plus 1 power plus 1 in our denominator. And then now we have this part, e to the cx to the 2k plus 1 power in our numerator. And we now have the denominator that looks the same as whatever we started off. And keep in mind, they're the same integral based on the King's property. So if we add these two expressions together, it means that we're just adding the same integral together, meaning that we are adding I to I itself to give us 2i. And then the right hand side will just be the integral in blue plus the integral in black. And let's see if we can combine anything. Well, yes, because they are actually going in the same interval from negative b to positive b. So if we add these two integrals together, we can just simply add the two expressions inside of each integral together. Moreover, we see that they have the same denominator. So in fact, if we put them together, it is the same as saying that we're adding the numerator parts together, and that's it. Now, recall that there is nothing but dx in the blue part. It just means we have 1 times dx. So we're adding the 1 dx to this part up here in the numerator. We get 1 plus the expression. Let me use this. E raise it to this. Okay. So last but not least, we need to check a few things. We see that those two are the same. We are thinking that we can cancel them out, but let's check it in case. So we need to make sure that we don't get any cases such as 0 over 0 or infinity over infinity. Well, let's see. Can we really get 0 over 0? Not really, because we know that e to the cx to 2k plus 1 power is always positive because we're raising it with a positive base. Good. So the denominator as well as the numerator will not be 0. We don't have the problem of 0 over 0. And are we going to get infinity over infinity? Well, that that would be true if our bound is unbounded, meaning that if we have negative infinity or positive infinity here, such that the numerator, not the numerator, such that the exponent part will have a chance to get positive infinity, so that we'll raise e to the positive infinity power to give us positive infinity for the expression. But since we already said that a and b are both real numbers, meaning that they're strictly less than infinity, no matter how big a or b are, well, b, there's no, we'll always get a finite value here, so that this expression e raised to such power is also finite, so that the expression in the denominator will never hit infinity either. Good. So we already checked that the two cases that we cannot cancel are not in this interval. So we can now do the cancellation. So since the numerator and the denominator are the same, after the cancel out, we just get 1 in the expression times dx. So again, we just have a very nice integral from negative b to positive b of dx. So we can just think that is a rectangle on the graph, and this rectangle has the height that is equal to 1 and the length is equal to b minus negative b, which is 2b. So the area would just be 2b times 1, which is 2b, meaning by dividing both sides by 2, we get the initial interval integral is equal to just 1b. That's it. So I hope you all enjoyed this video, and if you like it, please don't forget to like and subscribe to my channel so that you can find out more of my videos. Also turn on the notifications so that you won't miss any of my new videos either. I'll see you guys next time.